So the question is the center of mass, and this is how far we went. Well, this was the question that explains why we do the way we do it, and that is computing the sum of the moments of all the weights relative to a point that's unidentified at that time, and then find what that point is. If the restriction is this, the sum of those moments is 0. Okay, so these are moments with respect to the origin. This is the moments relative to the to point C. So the way it works out, as you can see, mass is multiplied by the lever. Okay, so once again, this is what we're seeing here is mass. Each mass multiplies by its particular lever. Okay, how much it pulls in a particular direction. Okay, so let's take this equation to begin with and try to do something with it. That is, let's just do it. Let's compute it and see how much sense it makes. Okay, so with Excel. So we're gonna just randomly or almost randomly spread out those weights on a string. Remember, this is still where everything. It doesn't have to be necessarily about seesaw. Okay, so it is a better way to think about it is once again back to a rod with a non-uniform distribution of weight, a non-uniform density, if you like. So, but for the time being, we think of it as if it is these pieces have the density is uniform within each of the pieces. Okay. Okay, like this. So each number, depending on the density, the number is assigned to each density, and then what matters in addition is the lever. Okay, so let's try to do that. So it's not dissimilar from this, what we're talking about, especially the way I have presented it is like this. It's over here, as you can see, as if I'm putting two equal size objects on top of each other, which already suggests that what we're talking about is a function. Okay, so depending on the location, there will be that value of the function indicates how much weight is concentrated at that location. Okay, so and then we are certainly going to discover shortly that indeed we're going to be doing integration again. So that's our last try with that. Okay, so let's do a new one. Okay, so I'm going to do it from scratch, but I need a bigger. Okay, so okay, just a minute. Width about 4. Okay. Okay, so let's see. So I'm going to be putting coordinates here. Okay, coordinates here. So starting with, I don't know, 3 and go on. I'm putting some number here that is abstract because so that it would be clear that wherever we put our coordinate system doesn't matter. It should produce the same result. So just as well start with 3. Okay, so and then I will proceed. I'll put H my step as I have done before. I'll say 0.1. Okay, and this is by how much I will be progressing from right to left. How many uniform pieces the rod is made from. Okay, or alternatively, you have a rod and then you're interested in a center of mass. How frequently you test the density or sample the density within the rod. Okay, so it will be equal to the previous one plus H, which is R2C2. Okay. Okay, and then I spread it out as many times as necessary. This is going to be my rod. This is not the rod just yet. it is rather the locations on the rod. Okay, I don't think I did it right. This is how it's done. Okay. Okay. Now the next row is the weights. Okay. So each location will have a weight. And here I can certainly manually enter numbers here. I just want to have something more regular, so I'll just put a formula here. Doesn't matter what it is. Say 2 plus 3 plus equal 2 plus say sine x. Doesn't matter what it is, and then we'll see if it works. Okay. So these are the weights. Whatever the units are, is our choice. Okay. So these are the weights. As you can see, they alternate a little bit, but not a lot. Okay. To see the rod, the way I did it, indicating with the color or grayscale the density, you could do it with Excel easily. So where is it? Oh, here it is. It's called conditional formatting. So colors. Where is it? Color scales. Okay. How about this one? Yeah, I think that I'll pick this one. Okay. So, okay, it's clear that green is denser and yellow is thinner. Okay, so that's your rod, and you can imagine that it is almost looks if you forget about the numbers, it looks pretty much like you're looking through maybe a piece of glass, and it varies. You can actually recognize the density based on how opaque it is, and the green one is less transparent than the yellow one. Okay, so that's all good. Let's do it one computation so that it will be absolutely clear what it is that we're talking about. And I'm talking about the weight. Let's compute the weight. The total weight. What's the total weight? Well, actually, let me correct myself. These are not weights. These are densities. Okay, so the density. So we sample the density of the rod at each of these locations, and these are the numbers that we got. So say, I don't know, pounds per inch, possibly. Okay. So how do we find the mass? How do we find the mass? It is the integral, right? So, but right now Excel cannot integrate. So, what do we do instead of integral when we just sum? Almost. So you got to actually, since I corrected myself. So these are not weights; these are densities. So in order to get the weight, you multiply the density by what? With the length, because this is a linear density, so this density is per inch of the rod, and so we don't actually look at the volume, and the length of each piece is 0.1 over there on the left. So so if I put here masses or weights, let's say weights. Okay, so I will multiply this number by, which is the density, times the length of that little piece of the rod. So I multiply by once again R2C2. Okay. Okay, so non-complicated, you multiply by, so you divide by 10. So the same thing as dividing by 10. Okay, and then I just to the total I put here total. Just add these. Indeed, it doesn't take more than that. I just want you to recognize that what we're doing here. So this one is equal to the sum of those. So I just highlight these, and that is my sum. Okay, so this the total is 3.6. As you can see, it's what is the actual? I mean, let's verify that it makes sense. The length of my rod is 2.6. 2.6 with the density varying between 2 and 1. Okay, so yeah, seems reasonable, right? Okay, so all right, so that's good, and this is this computation over here is nothing but the Riemann sum of that function that we have. Riemann sum width times the value of the function. Okay, so it's the Riemann sum of the density function. Okay, so but the interesting question is naturally the central mass. Okay, so for the central mass, remember we're going to need the levers. So let me do the levers. Okay, so which is levers with respect to the origin. Well, let's do levers with respect to, so I will put here C as a candidate, say C equal to, I don't know, by looking at it you cannot tell exactly, but let's say 4, why not? Okay, so suppose the candidate for our central mass is 4. Okay, so I'm going to be computing the levers relative to 4. So how? I just subtract, right? So I'll subtract what? I subtract the coordinate minus 4. Okay, so over here, the lever, it will be equal to the coordinate, which is this, right? Minus that entry over here, which is row 1, C5. Okay, row 1, C5. Okay, so as you can see, the lever is -1 because it is to the left of 4. So and the lever is negative. Okay, then on, and then I spread it out again. Okay, so these are my levers. Okay, negative up to 4. At 4, naturally, you have 0 lever. And the rest are positive levers. Okay, so the next one, what's the next one? The moments. Okay, moments. Moments are simply, remember, they're weights times levers. Okay, so more weight, more moment, and more lever, more moment. So I'll just multiply down. So it's equal to this times that. Okay, so once again the signs will be the same as the one of the levers. So if positive or negative, depending it's to the left or to the right of the origin. I'm sorry, F4. Okay, so total moment. Let's compute the total moment. No, there's not. Okay, so my answer is 0.5. What does it tell you?
It's not balanced.
It's not balanced. Okay, that's true. It's not balanced because you're supposed to have 0. Can you say anything more than that? Which way is it going to tip?
To the right.
To the right, yeah. It's going to tip to the right because so the positives beats the negative, so it will be pointing up, tipping to the right, so to the positive. So okay, so what do we do? What do I do then? I could try to, by trial and error, I could actually find the center of mass. So replace 4 with what? Suggest something.
4.2.
Okay, 4.2. Negative 0.2. Okay, trial and error will just, now it's tipping to the left, but not as hard. Okay, so 4.1 seems natural. Okay, so increase more, 4.15. Well, close enough. Okay, 4.15 is indeed the center of the center of mass. So if I put my finger here, work. So if this is the rod and my support is here, then it should balance more or less. Okay, so it might be a bit hard to actually confirm the results like that, but certainly, well, we can count on that. That the answer is correct. But certainly questions could be asked to confirm it in kind of more theoretical way, and some of the objects are known to be balanced equally if for example there is symmetry. So if there is a same distribution to the left and to the right of a certain location, this exact same distribution of weights. Okay, then the center of mass will be in the middle. Okay, so for example, if that middle is 0, what kind of function are we talking about? Symmetric, same to the left and to the right. What kind of function is it?
Quadratic.
Quadratic is good. X squared would be good. What about fourth power? Looks the same, pretty much. What if it looks like this? Well, I'm talking about symmetry, so what? Do you remember the name of that type of function? Even functions, right? So same exact symmetry. Not only the same exact amount to the left and to the right, but they totally exactly follow their own shape. So then the center of mass will be at the origin. Okay, so for example, if you have a circle or a semicircle, then it will be balanced on the center. Before I continue, I might have seen this somewhere. Have you seen this? Look familiar? Well, some see. So this. So that's the balanced object, third-dimensional object. So we're talking about here. We're talking about density and distribution of weight along the rod, and here it is the distribution is three-dimensional, and as you can see, an object obviously also will have center of mass. And just looking at the picture, like this, you can tell where the center of mass is. Anything. So look at the symmetry. So the center of mass will be located here somewhere on the axis of symmetry of the bird. Okay, and then there's presumably, since it's here, so it's not tipping. So it's not tipping left, right, and if I tip it, it will come back, right? So that means that indeed this is one of the axes of symmetry, and one of the that's where the center of mass is. I also, if I tip it this way, it's also comes back. So once again, so it's a bounce this way again. So indeed, if I look at it vertically, the center of mass is at the beak, at the end of the beak. Okay, but that is only two-dimensional problem. So where is the third dimension of the center of mass? So is it below or above or exactly at the beak? Above, below? Who think it's above?
No, wait.
Below? Below? Or exactly at the beak? No guesses. It is below because it's so stable. So it's located below the support, and that's why it holds its position so well. You need some physics to explain it, but you can imagine that if its center of mass was here, right at the top of the head, it would be easy to tip it and it would fall. Okay, but if it is below, it swings underneath, and well, it's like think about like a pendulum. Not a pendulum. If you try to balance anything on your tip like this, it's hard. It's hard. Why? Because the center of mass is here, right? Even if suppose I have a hinge at the end of the finger, even then it would be very hard to hold it because it will be falling. But if I have a hinge and I'm holding it like this, then it will be stable. Okay, so when I tip it, why? Because the center of mass is below the point of support. So that requires three-dimensional analysis, but the analysis is very much in the same, done in the same manner. So, well, it's just takes 2 extra dimensions to study. This is just one. In a way, it is. I'm not sure if it is uniform. I think it's just a piece of plastic. So this one has uniform density. It is then the complexity of its shape, but there are its dynamics or statics, if you prefer, comes from its shape, not from the distribution, not the various distribution as we have here. So in other words, we are studying in a way as if this is a two-dimensional object. So let me explain what I'm talking about. So this one is visualized as a rod with the variable density visualized by different color. But I can also just simply plot this. Another tool of Excel. I can plot I could have a bar chart. A bar chart like this one. That's not right. A bar chart. Maybe this one. Yeah. Okay. So certainly we can think of this simply as a function that varies of the density that varies from high to lower and then high slightly higher. On the other hand, think about it. Instead of thinking about an object like this, a rod with variable density, you can think about it as if it is made of this kind of piece. It is. I'm not sure if. Well, imagine that this piece is cut from a piece of paper. Magazine. So, okay, so a piece of paper, and you cut. Well, let me try to reproduce it. Okay, so suppose this is a graph that I have over there. Roughly. Okay, so I could try to balance it like this. Okay, so this is facing you. So where the balance is, it's roughly not in the middle, a little bit to the side. So it's very hard to balance because, well, obviously, the main reason is because it's so flat, it will floating in left and right. So I cannot really balance it. But you imagine that the only question really is to put my hand or my finger right under the 4.2 location, and it will be balanced as long as, well, I'm skilled enough. But anywhere else off 4.1, it will tip left or right. Another way to do it is to balance it. Much easier on me is try to balance it on some flat ridge like this. Okay, so in other words, I put that piece of paper which matches that graph over here, maybe like this. Okay, and then instead of holding it like this and trying to balance it on the edge, I will put it flat, and then I'm balancing it not on the edge, but the whole thing. So say maybe like this. And once again, if I put it in the right position, then I'll have balance. If I put it slightly off, it will slide. Okay, so that's roughly how it works, and that way we transition from a non-uniform one-dimensional object to a uniform two-dimensional object. Okay, so then as you can see, the density is assumed to be the same, just like that piece of paper. The density is the same everywhere, and so we don't have to worry about it. And then once you look at this picture, you recognize this as indeed the Riemann sum of the sum of these is the mass, the total over there, 3.6, and that is simply the Riemann sum. With these are the heights, the widths. You can guess what they are. 0.1, and it give you the whole weight. Okay, so let's take another look at the formula that we have. The formula is this, right? So after we defined, you can think of this as the definition of the central. No, not this, the definition, but this is the definition of the. It's a balanced equation, and C is the definition of a center of mass. Is that C that satisfies balanced equation, which we exactly carried out. So whatever follows, we didn't use right now. We took the equation of the balanced equation relative to C, and then found by trial and error, by just reducing the, making smaller and smaller step, left, right, and found such a C that gives us indeed the zero total moment. Okay, but then you can certainly verify that it works out that the total moment divided by that C is supposed to be the total moment divided by the mass. Well, let's verify that. So remember the answer is 4.2. Let me copy this. Okay, so what I'm going to do is I'm going to put C0. Okay. And so then certainly it's not balanced anymore because as you can see the whole rod starts at 3, so it cannot possibly be balanced. The weight is the same, the total moment is 15, and then the formula is, well, we just saw this formula, the location is supposed to be, I thought I wrote this somewhere. It is the fraction of, see, the total moment divided by the total mass. So those two numbers on the left that we have here, total weight is this, total moment is this. We just have to divide. Total moment divided by total weight. So it will be over here, I'm just writing it, it's equal to this divided by that. Okay, as you can see, it's 4.1 as predicted. So we found the same number by trial and error, but that formula gives us the answer even easier. Okay. Okay, so where do we take this next? The next is, I already suggested what it is about. It is about Riemann sums. Everything in this chapter is about Riemann sums. It's just we just have to recognize them. So you have to introduce a function explicitly, and then recognize where your Riemann sum is. So the shape, or rather the density, is already a function. We just need to see where our Riemann sum is, and unfortunately, the Riemann sum, the denominator is the Riemann sum, but not the numerator. The denominator is the Riemann sum of the density. So let me work that out. Okay, so I did it already with Excel, so now let's start over. So, suppose say y equal L of x is the density at location x. Okay? And then we keep going. We then yeah. So locations, there aren't too many locations. We have say x1. No, the I want to have Riemann sum. So so they're going to be C1, C2, C3, Cn. Well, actually, I have a picture here somewhere. Here it is. Well, actually, let me show you the picture that we looked at yesterday. This is the original picture that we looked at yesterday. So you have the rod, you divide into pieces, you sample that those are x's, you sample the density with c's, and that creates a function. You create from that function, you create the Riemann sum on the right. The total is then the approximated weight. Okay. Now we do something different here because we're not interested in weight anymore. There are no levers here. Okay. So we do the same construction but just with the levers. Okay. So once again, we cut our rod into pieces. We sample the density every time. We still have new function, and then on the left we have the Riemann sum of L. So let me write that, make that clear. So Riemann sum of L of x, the density. Okay. In the meantime, but that's just the denominator. The numerator involves levers. So those red bars, I meant to have them as levers. So this is still my 0, which is not really a center, but I'm looking at the levers with respect to 0, and those are those black bars. So those I have to multiply. You can actually, well, what I have here is, in a way, look at it. It's like once again, a seesaw with one support, and then kind of I don't know, some kind of buckets of water of different width and height are standing there, and we see if they balance. So it's almost like that old-fashioned scale, you know, and we're trying to balance that. That's how they used to weigh things. You have two cups, and you put your, I don't know, vegetables on one, and you put weights on the other. So that's almost exactly what we're doing there. And then the levers are the same, and that's why the weight was the same, if this balanced correctly. So as you can see, the denominator then will look slightly different. It will be, well, let me point that out. It will be, for example, for this one, this, no, it doesn't work. Let me try again. Okay, so this one, nope, there is no color here. Okay, so let me try nonetheless. Okay, so this bucket, not this bucket, this bucket, okay, it is has to be multiplied, its weight has to be multiplied by this lever in order to have its moment, and then the total moment will be the sum of those. So let's write this out. Okay, so function, density, delta x's suppose have been supplied, and then what I do is I create Lx, L of C 1 times delta, well, now first multiply by the lever first, so it will be x minus C1, and then by delta x. Okay, so it was m sub 1 times delta x. So that is the, that's what I meant to say here, m times x minus C1. So this is the moment of the first object. So C1, the first object, the first mass, first weight, multiplied by the first lever. But if we now express in terms of the density, it will be density multiplied. I didn't put it in the right order. Let me put it this way. So what is the mass if not the density multiplied by the width of the interval? Okay, so this is a moment again, and then total moment is the sum of these. So L C sub I delta x, x minus C sub I from 1 to n. So once again, that's what we just saw. C runs from C1, C2, C3, C4, Cn. And intervals and points. Okay, so that is our sum, the total moment, and we want it to be equal to 0. Okay, so the trouble is, as I pointed out, this is not a Riemann sum of any function. Well, it is actually a Riemann sum of a function, but not the one that we prepare to deal with. The only function that we know is L. Okay, so this is not the Riemann sum of L. So let's just jump straight to our restriction. So then C is equal to no, I'm sorry, I messed it up over here. That's not right. It is Ci minus C. Ci minus C. So Ci, and then there is the location of our C, the support somewhere else. And so we are take the coordinate of our weight and see where what the lever is. Okay. Okay, and so then we solve this equation for c just as before, just the equation becomes different because now function L is involved. So in the numerator we have simply our sum of the moments with respect to c, with respect to 0, okay, so delta x, ci over here, ci delta x, and denominator is the true Riemann sum of the function itself. So you can compare to appreciate the difference that little term over here is the only difference between numerator and denominator. So and that is, what's the difference? The difference is the lever. So in the denominator we have mass times the width. So all these little pieces are added together and you have your total mass. Okay? At the top you're not adding the masses, you're adding the moments. And that extra ci over there is what creates that moment. Okay, so altogether they are, however, both are Riemann sums. So these are Riemann sums. Well, in fact, let's say Riemann sum of this one is a Riemann sum of L, and the other one is L of x times x. Okay, Riemann sum of L, so the density sampled at those particular locations. For the denominator, for the numerator, we sample both the density to begin with, but we also take the lever. Okay, so that's why the function is different. Okay, but we already did this with Excel, so that is not surprising to us. So that's certainly working out. We are progressing then to the next level, however, and that is the level is a function that is now changing continuously. Okay, so suppose y is equal to L of x. This is a continuous function. Then we are not. We are our analogy with the seesaw and objects located on top of it, it fails because as I said, the change is now continuous. So it's quite literally this is how it's changing. The density is changing continuously rather than incrementally. And so how do we deal with that? It means that there are infinitely many weights, but they are infinitely small. So in that. Certainly not entirely new. That's what we saw here. As we make those intervals smaller, the height becomes, those bars become thinner, and the end result of what happens to those Riemann sums, they converge to the Riemann integral if the function is well behaved. So in other words, let's try to draw a conclusion from this. We're drawing a conclusion from the balance equation, which is this, and then we'll try to draw a conclusion. What is the corresponding conclusion about the function when it is continuous? So in other words, we are refining those partitions of our interval, and not only in terms of the not only in terms to determine the weight, that will be giving us better and better estimate of the weight as those x's are smaller and smaller, but it will also give us the better and better moments. And the trouble is, of course, you have infinitely many weights, infinitely many moments as well. So both of the sums will turn into integrals, and so I will do that with the balance equation. So then suppose we have a continuous function and we have a sequence of partitions with delta x going to 0. Okay, so or same as to say n goes to infinity, delta x goes to 0, so they become infinity thinner, there are more and more of them. Okay, then what happens to the balance equation? Well, you need to recognize that this is indeed a Riemann sum, except you have to, I have to rearrange the terms again, but you can see that delta x is the term that we have to, that is the term that turns into dx. Okay, so as long as we know what we're talking about here, we have the Riemann sum of the function that's left. So that Riemann function is, okay, so let's see what we're getting here. So then the balance equation is, if L is integrable, if f is integrable, then the balance equation is, well, so what happens is certainly the same thing as it was always. The sum turns into an integral, and well, there will be one integral, a definite integral, so it will be integral from a to b, and then we just have to say what the function is. The function will be Lx, x minus c, dx, and it's still equal to 0. Okay, so that's our new balance equation. Presented for integral, in terms of integral of the function rather than summation. So it always starts with summation. You can, well, if you practically speaking, if you have a rod and you want to find its balance center of mass, and you don't want to actually physically try to find a balance for experiment, what do? You sample the density. You literally sample density if possible, if it varies, and then put it in a spreadsheet. And then you don't do this. You don't need to do integration because, well, what is the point? It's going to be summation anyway. So you do summation. You have the center of mass by that formula that we already used. It is when you have doing something more theoretical, and maybe you don't have an actual rod, but rather what you have is you're planning to build a rod, and then you have some kind of theory about what kind of or plan how the weight will be distributed through it. So it might be, as we discussed yesterday, it might be linear, or it may be changing in some weird way, maybe whatever, you don't know. It's your design, in fact, so you might be the opposite problem. Maybe you know where the balance should be, and you balance point, the center of mass is, and you try to design a rod around it in such a way that it's going to have, it would be balanced on that location. So then you do integration, right? So you have some kind of function that will represent, according to your theory or plan, represents the density, and you integrate it in this fashion, and you have your equation for the center of mass. Fortunately, we don't have to do experimentation as we did. It works out fine if we just rearrange terms here. So I'm using the sum rule of integration, and this thing breaks into two: integral from a to b, Lx dx. I'm sorry, x. Okay, minus integral from a to b, Lx c dx. Okay, so we're doing, and it's equal to 0. We're doing the same thing, just like we have sum rule for summation, we have sum rule for integration, and the one integral breaks into two. I rearrange terms. So for c, as you can see by the constant multiple rule, the c will drop out of the integral, and then what I have here is a formula that is almost identical to the original, and so what is it? It's once again integral Lx x dx from a to b divided by integral from a to b Lx dx without x. Okay, so once again I'm pointing out at the difference between the two formulas. The lever is in the numerator, not in the denominator. And if you think about the units, then they match, right? So because all the units will be canceling out, whatever the how you measure densities. As I said, pound per inch, for example. That is the if you integrate over all the distance, you will have pounds. So the denominator is measured in pounds, and the numerator is measured in pounds pound inches. Right? So that extra x in the numerator, that's why the numerator is measured in pound inches, and when you cancel out, the end result is inches, and that's why c is measured in inches. So that's just a way to confirm that everything works out. So then once again, c is the center of mass. Of what? Let's make it clear. Center of mass of what? So we used to say just the center of mass of a system of weights. That was good, but now it's not a system, even though there are many weights, but there are infinitely many. So why not be specific? It's the center of mass of the region. This is what I'm talking about. AB, and we found the center of mass here somewhere. This is my C. It is the center of mass of the region under the graph of the density function of the region under the graph of the density function. Okay. I may have another picture here. Here. Okay, so starting point was the rod, as you can see, and we were looking for one single support that will balance it, but we ended with identical. Answer is identical, even though what we're trying to balance is once again an object cut from the graph. So, or rather, graph cuts the piece of the xy plane, whatever lies below, between the graph and the x-axis, as well as the two ends of the rod. Now, I have only one thing to add to that before we move on. Why it is so important? Because, well, with all due respect to physics, this is mathematics. So, which means that the physical things that which we've been talking about for a whole 2 days are just single manifestations of other things that can happen, and this will be very meaningful interpretation and analysis. So this is what I'm talking about. No physics, right? So there are no weights, no nothing, and what we're interested in, what are you saying here? What is it? You've seen before?
Precision and accuracy.
What?
Precision and accuracy.
No, I'm not sure. I don't think so. But let's stick to the language that we have, and that is, well, I was asking a question about the practical importance of this, and well, actually, I have another picture, and then maybe it's become clear what I'm talking about. There is another target here. Here it is. Okay? If you compare the two, what is the point? Where is it? I lost it. So can you compare the two pictures? The black one and the yellow one. What's the difference? Well, look at the yellow. Look at the yellow. Where's the yellow? Yellow is gone. Okay, so what do you say about that kind of shooting?
They didn't do as well as the other one.
No, maybe not. But what is so special about it? He did not do better, but the problem is that it's off center. The other one has actually, I wouldn't say that necessarily the other guy did so much better. Look at it, but it was centered at the bullseye. So, can you draw a conclusion about the second guy? He might be just as good a shot, but the sights are off. The sights are off. Look at the group. The group is good. It's just off. So probably these sights are off. That's all you need. So finding the center of how much the sights are off is the problem of the central mass. Okay, so I'll mention that next time. Okay.